We've looked at the behavior of single capacitors, individual capacitors, and how their charge and potential differences interact, and how we can describe the capacitance of that capacitor, how we can describe the relationship between the charge and the potential difference. Now let's talk about what happens when we do that for combinations of capacitors. What happens if we've got a whole bunch of capacitors all sort of jumbled up together? We've got this capacitor here and this capacitor here, and look, they're wired up, and then maybe we have it, and we could just make this crazy complicated, right? And then the question is, how would they behave overall if we look just at the terminal? If we just say, all right, here's this big combination of capacitors, and we say, I don't know what's inside of here. I'm going to look at this terminal and this terminal, what goes in and out, and can I say something about the behavior of all of those capacitors together? And we're going to simplify that by thinking just about pairs of capacitors, and we can expand that up to more complicated situations, but we'll think first about what if we put our capacitors in series, and what if we put our capacitors in parallel. First, let's address capacitors in parallel. So here are two capacitors that are in parallel, and we want to ask about what happens with the charge, what happens with the potential, and what can we say about the overall capacitance, the equivalent capacitance of this situation. So first, let's look at the potential. Suppose we have our two capacitors, and we put a voltmeter on one side and wire up and say, oh, what's the potential difference across this capacitor? And then we take another voltmeter over here and we wire it up and connect it up, and we say, oh, what about this capacitor? And I hope that you can see very quickly that these two, this wire here and this wire here, they are both connected with nothing in between them, so they are essentially at an equipotential. And this wire here and this wire here also essentially at an equipotential. So what that tells us is that if maybe this is capacitor number 1, whoops. This is capacitor number 1, this is capacitor number 2, that the voltage over capacitor number 1 should be equal to the difference in potential over capacitor number 2. And those two things are also going to be equal to the terminal voltage, that if we just look at the behavior of those capacitors just in a box together, we look at the terminal voltage, that'll be the same as the potential over any one capacitor. When I say terminal voltage, I mean we're going to imagine that we've got this combination of capacitors and that they're inside of a box, right? And that we don't know anything about what's in the box. We can just look at what's going on at this terminal and what's going on at this terminal, and that we can measure the voltage from one terminal to the other terminal, right? That we might say, okay, what's the voltage there compared to the voltage here, and we can measure that out, but we don't know what's going on inside. That's gonna give us a way of thinking about what's the equivalent behavior. But in this case, what we find out is that the terminal voltage is the same as the voltage over either one capacitor. Now let's think about the charge. So charge flows into our capacitor combination, right? And some of our charge is going to go to this plate, and some of our charge is going to go to that plate. Now, this drawing is symmetrical, but there's no guarantee that these two capacitors have the same capacitance. We do know already that they have to have the same potential difference, but that doesn't mean that they have to have the same charge. So some charge, Q1, is going to flow over to the left, and some other charge, Q2, is going to flow over to the right. And at the same time, we're going to have charge flowing out here and out here. Well, I hope you can convince yourself by conservation of charge that the amount of charge flowing in right here into this junction has got to be the same as the total amount that flows onto this capacitor plus the amount that flows onto that capacitor. Well, that gives us a second crucial statement to make about this combination of capacitors in parallel, which is that the terminal charge, the charge flowing into the combination, has to be the sum of the charges on the two capacitors inside. So with these two capacitors in parallel, we have two key ideas. One of them is that oops. Okay, so with capacitors in parallel, we've got two key ideas. One is that the potential difference over the whole combination is the same as the potential difference over any one, and that the charge on the whole combination is the combination of the two charges. So using that, we should be able to compute what the equivalent capacitance of this this combination is. We want to say that the capacitance of this combination, the equivalent capacitance, is going to be, well, we can just use the definition of capacitance. It's the charge on the combination, which I'm going to say is the terminal charge, divided by the potential difference on the combination, which is the terminal voltage. Well, we know that the terminal charge is Q1 plus Q2, and we know that the terminal voltage is just either one of these voltages, right? We could have it could be voltage 1 or voltage 2. I'm going to just put voltage 1. We can separate this out and say, oh, now that C equivalent is going to be Q1 over, I could either say voltage 1 or voltage 2, and I'm going to say voltage 1 to make this fraction consistent, and I'm going to say Q2 over, I could say V1 or V2, but I'm going to say V2. They're all the same. And now notice this right here ought to look really familiar. Q1 over V1, well, that's just the capacitance of our first capacitor. And the same for the other capacitor. So I could say that the equivalent capacitance is just the capacitance of capacitor number 1 plus the capacitance of capacitor number 2. And I'm not going to go through the, not going to work it out, but, if we have more capacitors in parallel, we could keep on going on, right? We could say, C1 plus C2 plus C3 and so on. What about capacitors in series? Well, let's take a look here. First of all, let's talk about the voltages. And again, we'll say this is going to be a capacitor number 1, and this will be our capacitor number 2. And let's take a look at the voltages. Well, we can have some voltage difference here, and we can have some voltage difference here. I hope you can see right away that there's no guarantee that these two have to be the same. As a matter of fact, if we want to look at the terminal voltage, the voltage from one end of our combination to the other end of our combination, what we're looking at is the sum of these two voltages, right? That we're going to have a potential difference from here to here, and then we're going to have another potential difference from here to here, and those two things are going to add up to give us a terminal potential difference, so that we can say that the terminal difference, V terminal is equal to V1 plus V2. Now let's talk about the charge. And the charge is a little bit less obvious. So we push some charge onto here, and it flows onto the top plate of this capacitor. And remember that capacitors as a whole have to always stay neutral. I get some charge on here, but in order for that capacitor to stay neutral, we have to push some charge off of that bottom plate in order to keep the whole capacitor neutral. We have to put some positive charge off, leaving a negative charge behind. How much has to get pushed off this bottom plate? Well, the same amount that we pushed onto the top plate in order to keep this capacitor neutral. And so some positive charge is going to get pushed off the bottom plate of the first capacitor and pushed onto the plate of the next capacitor. And the same thing is going to happen there. This is going to become negative because we pushed some charge Q off of there. So each one of these capacitors is net neutral, and in addition, you can see that this section, like if we take that top plate, the bottom plate of the top capacitor and the top plate of the bottom capacitor, that also, this had better be net neutral. We would be in trouble if this weren't net neutral, right? But here we've got a negative Q, here we've got a positive Q, because notice that this chunk of conductor here is really electrically isolated. If we started out with that neutral, it better end with that neutral. So overall, we've pushed some charge Q onto the top. The same amount has gotten pushed from here to here, but really the total charge in here hasn't changed, and we've put some charge Q off of here. What does that mean? Well, that means that the terminal charge that we've pushed on is the same, Q terminal, is equal to the charge on the first capacitor. And that's equal to the charge on the second capacitor. So that gives us two principles here for capacitors in series. The first is that the terminal voltage is the sum of the voltages on the two individual capacitors, and that the terminal charge, the charge that goes in or out of the terminals of the combination, is the same as the charge on each individual capacitor in the combination. Okay, so now we're ready to find out the equivalent capacitance. Well, the equivalent capacitance is found out from the definition of capacitance, which is how much charge does it take to get a unit amount of potential difference. And so the CEQ here is going to be the charge on the combination, which we said is the same as the charge on either one of these. So I'm just going to write Q1 here, divided by the potential difference of the combination, which we said is the sum of the two potential differences, V1 plus V2. Now, this is we can't do quite the same simple algebraic trick that we did last time because the denominator is a sum instead of the other way around. So we're just going to take the reciprocal of both sides. I'm going to say 1 over the equivalent resistance is equal to the sum of the voltages over the charge on either one. I'm just writing Q1 here. And now we can separate this fraction out, and we can say, okay, that's equal to V1 over Q1 plus V2. I could write V2 over Q1, but I know that Q1 is the same as Q2, so I'm just going to write Q2 here. And that's 1 over CEQ. And notice that what I have in each one of these terms is the reciprocal of that original capacitance, the reciprocal of of capacitor 1 and the reciprocal of capacitor 2. So this tells us that 1 over the equivalent resistance is equal to 1 over capacitor 1 plus 1 over capacitor 2. And if you have more than two capacitors in parallel, you can keep on going. You can say 1 over capacitor 1 plus 1 over capacitor 2 plus 1 over capacitor 3, and so on. So here's a quick summary. We say that if two capacitors are in parallel, that the voltage on the combination is the same as the voltage drop over any one capacitor. Notice that's not the same as in series. In series, the terminal voltage is the sum of the two voltages. When we look at the charge, the overall charge on a pair of capacitors in parallel is the sum of those two charges, and the overall charge when the capacitors are in series is the same as the charge on any one capacitor. And then we do a bunch of algebra, and we say that the equivalent capacitance of capacitors in parallel is just the sum of the individual capacitances, and the reciprocal of the equivalent capacitance in series is the sum of the reciprocal of the individual capacitances that are in the combination. You may have noticed already that this is the opposite of what happens when we combine resistors. Resistors combined in series are just the sum of the resistors, and resistors combined in parallel are, well, the reciprocal of resistors combined in parallel is the sum of the reciprocals. So capacitors in combination look just like resistors in combination, except for flipped around. It's really worth memorizing these two things. And this conceptual stuff is also important to be able to use, because it's not just for how to do the derivations of these results here. So the important things to know about combinations of resistors in series and parallel. And of course, you can assemble a list to do much more complicated combinations of resistors.